All right, so section 40 is on the fundamental theorem of calculus. So we talked about why it's called the fundamental theorem. It's like the most important theorem in calculus that relates first semester of calculus to second semester, right? Derivatives to integrals. So basically, for a long time, people were finding equations of tangent lines, and they were finding area under a curve, and they didn't realize that these two concepts were related. And then they were like, wow, oh my gosh, it's just an antiderivative, the opposite of a derivative, okay? So this is the fundamental theorem of calculus, and there's two parts to it. So the first one says, if I take the derivative of basically, or not the derivative, the integral of a derivative, I get its antiderivative. So if I have f of x in here, when I integrate, I get capital F, okay? And this is exactly what you guys have been doing on your homework for the last couple days. So in this case, it would be like 1/3 x cubed. You do the antiderivative minus x squared, going from 0 to 2. And then you find the answer by plugging in the 2's, and then plugging in the 0's and subtracting your two results. So I'd get 1/3 times 8 minus 4, and then minus 0. So I'm going to get 8/3 minus 4, which is 8/3 minus 12/3. So I get negative 4/3. Okay, and same idea for this one. We could just rewrite it. So we'd be like, oh, well, that's really just finding the integral of x the 1/2 minus x the negative 2. So if I do that, I add 1 to the powers. My new number out front would be a 2/3 minus I add 1 to the power. My new number out front would be 1 over negative 1, which is just a negative 1. And then I'm going from 1 to 4. So I plug in the 4. And hopefully you guys know how to do all of this without using a calculator. So you know how to do things like 4 to the 3 over 2, right? And 1 over x is x to the negative 1. So this would be 1 over 4 here. And then subtracting out, luckily I have a 1 for the next one, so it's just going to be 2/3 minus a negative 1, so plus 1. What is 4 to the 3 over 2? 8, yes. So we do 2/3 times 8. So I get 16/3 plus 1/4 minus 2/3 minus 1. So sometimes if you wait to combine your numbers, like notice how I have a 16/3 and a 2/3, I would combine those. Those ones will pretty much always have that same denominator unless you've reduced it, right? So I have 16/3 and then minus the 2/3, so I get 14/3 there. And then I could combine like the 1/4 and the minus 1. That would be negative 3/4. And then combine. Do you guys remember the little trick for fractions? Kinda. So you're going to do 14 times 4, because that's the same as multiplying by 4 over 4, right? So you get 56 minus 9. So 56 minus 9 is 47 over denominator 12. So this should be 47/12. You don't like that method? So much faster.
No, why couldn't it be 48 over 12?
Wouldn't that have been nice? I just didn't plan for it to be 48 over 12. Sorry. All right, so when you see something that says, like, find the area under the parabola from 1 to 3, right, we're going to find from 1 to 3. Okay, and we have lots of methods that, like, approximated this, right? So we could find right hand, left hand, trapezoidal rule, all this stuff. Okay, but we're not going to do any of those methods, right? We're going to actually find the exact area. And we do this by integrating. So you would have negative x squared plus 4x minus 3 going from 1 to 3, right? And you could find that. We also learned the glorious math 9. So let's use that. So sometimes on your homework I'll say you're allowed to use math 9. Sometimes I'll say that you are not. So if I don't say anything, you can use it. So if I have negative x squared plus 4x minus 3, and I'm going to go from 1 to 3. So your calculator might be updated. You might actually see the integration symbol. Mine still says f in int.
So you do the x first and then the negative 1 and then the 3? Okay,
Yep. So it's like x goes from 1 to 3. So we get 4/3. So that is the exact area under the curve. And you could do that with, remember our sigmas that we just did one time? Well, we didn't do it one time. We did it for a while. You guys took a quiz on it, and we're like, okay, you don't have to worry about this anymore because now we know integration. Okay, so we could have done this with sigmas. We would have gotten 4/3 as well. Okay, but you could also have some pretty tricky ones to integrate, which is why I've been drilling you with derivatives drills, for such a long time. So you should know what gives you a derivative of secant squared. Hopefully you all do. So it should be tangent. So in this case, it would be tangent of x going from 0 to pi over 4. So you'd be finding tangent of pi over 4. Do we know that? Minus tangent of 0. So I get 1 minus, and then tangent of 0 is 0 because it's sine of 0 over cosine of 0. So we get 1. So tangent of pi over 4 was just like the square root of 2 over 2 divided by the square root of 2 over 2, right? Sine over cosine. All right, so we feel pretty good about those? All right, so let's look at some AP type questions that would involve this. So number 5 says oil is leaking from a storage tank at a rate of R of t, which is negative t squared over 12 plus 100 gallons per day. Okay. So when I'm graphing this, my y value is in gallons per day. And this was our R of t. It was a rate, right? Do you guys agree that it's a rate when you say something like gallons per day? And then the other part is t, which is our time. So that's going to be in days. So it says graph the curve on the coordinate plane to the right. So they actually have this little grid for you. And so for graphing it, we would use our graphing calculator. Should we know what it looks like? I think this one we should know kind of what it looks like, right? Cole, what's it look like? It's a downwards parabola.
Yeah.
What's its y-intercept?
100.
100, exactly. And so notice how they've given us this grid. So our t values were from 0 to, mine got cut off a little bit, what's it say? 0 to 20 days. And then our gallons per day, our R of t, it goes all the way up to 200. So what would I do? I would probably adjust my window, right? So I'm going to make my window, my x's go from 0 to 20, like this grid has. And I'd make my y's go from 0 to 200. Let me graph it, and you can see that it's part of this downwards parabola. Okay, everybody have their calculator out. Did you all put that in for y1? I'm going to do a lot of stuff with a calculator on this problem, so I would put that in for y1. Okay, so wherever 100 is, I'll know where it is, somewhere around there. Then we have a downwards parabola. And it doesn't have to be perfect, but something like that. So part B says, how much oil has leaked out by the end of the 5th day? Okay. So Mr. Crawley always says units are the key to life, and I agree with him. Units are the key to life. They're definitely the key to calculus. Okay, if I'm trying to say how much oil, what will my answer be in terms of? What units will I have? Gallons. Will I have gallons per minute? No, I'm going to have gallons. Right now I have a rate. I have gallons per minute. That is a derivative in a way, right? It's a slope. If I want to go backwards to get gallons, what do I need to do? The antiderivative. I need to go backwards, right? So I want to find how much is leaked out by the end of the 5th day. In other words, I want to find how much oil over those first 5 days has left. And remember, always write it in the easiest way. So I would write it R of t dt integrated from 0 to 5. So let's do a real life example so you guys can think about this. Okay, let's say I have a water tank, the Carmel water tank, and it is losing, there's a hole in it, it's losing 100 gallons every single day. Over the first day, you would have lost 100 gallons. Over the first 2 days, you would have lost 200 gallons. Over the first 3 days, 300. Does this make sense? So if I'm integrating, I'm losing 100 from 0 to 5. I would end up integrating, and I'd get negative 100x going from 0 to 5. That would be negative 500. Does this make sense why we're integrating this? And our units would be gallons. The reason our units are gallons is because what this is it's finding an area. It's actually from 0 to 5, right? You don't have to draw this, but from 0 to 5, 1, 2, 3, 4, 5. It's finding this area here. And each of those rectangles that are involved in this have heights that are in gallons per day and widths that are in gallons. Everybody think about that with me. Gallons per day multiplied by, not gallons, multiplied by days, right? The width's in days, not gallons. I don't know why I said that. So our days cancel, and we're left with gallons. Does this make sense? On the AP test, this is a crucial skill, like thinking about these things, like saying, well, what units do I have? Okay, well, if I want gallons, I need to multiply by days in some way. Oh, multiplication. Well, that's the area of a rectangle. Rectangles make an area, so area is integration, right? You're going through this whole process. Okay, so we're going to find how much has leaked out by the end of this day, and we're going to use our calculator to do all the work for us. Does everybody have that first thing in for y1? So look under our y1. Do you guys all have negative x squared divided by 12 plus 100? I don't want to type that in again. I already typed it in. So we have something really handy on our calculator. Turn off the light so you guys can see the screen a little bit better. Is that really, really dark now? So what we're going to do is we're going to go to our main screen and do your Math 9. So go ahead and do Math 9. If you can see your buttons on your screen, it's so dark in here. And then we want to put in that function, but I don't want to retype it because I already typed it once. And this isn't a hard function, but imagine a really difficult function with lots of parentheses. So what we're going to do is we're going to go to vars. Do you guys see vars? It's underneath the arrows. So vars, it stands for variables. I want my y variable that I put in, so go over to y vars, hit function, y1. Anything that you haven't typed into y1 is not going to go there. So we're saying integrate the y1 function, and then we say from x values of 0 to 5. So we still do our 0 to 5. Hit enter, we get 496.528. And our units are gallons. I did this the other day in first period too. I kept writing galloons like balloons. It's like, I don't know why I keep doing that. Gallons. Does this make sense? Okay, we're learning all these calculator tricks. Got a lot of them. All right, so C, how much oil has leaked out between the 5th and the 10th day? So same idea, but now we're doing 5 to 10. And we still have our R of t dt. Okay, and then we're going to go on here, and even if you have those old calculators, like Ari was complaining that his isn't updated, you can do second enter, and you can replace what it brings up the last entry that you had, and you can now make it say 5 to 10. So your calculators, if they're updated, you can probably just go up and grab that whole equation and hit enter. So you don't have to keep typing it in. So we have 475.694. So it says, why is this answer less than part A, or part B, I mean. Okay. Why do you think it's smaller here? 5, 6, 7, 8, 9. Why is this smaller? The curve is closer to the x-axis. That's a great way of saying it. So R of t is closer to the x-axis, or you could say R of t is decreasing, right? Doesn't that mean it's getting closer to the x-axis? That's exactly why. This will actually happen in real life. If I gave you that water tank example and it has a hole in the water tank, I'm not going to lose 100 gallons exactly every single day. Okay, think about the real life situation. I know Cole's like jumping. He wants to answer this. My physics people love this type of stuff. Why is that? That at the very beginning, I'm actually going to lose a lot more per day than at the very end. Have you guys ever seen a bucket that's like full of water and it has a hole in it? Okay, at the first bit, it's losing a ton. It's squirting out really, really fast. Right, and then at the end, it's kind of trickling out. Why? Ah, that's exactly it. Less pressure. Good. Because there's less weight on top of it, right? The heavier the water is on top of it, if the hole's at the bottom of the bucket, right? If the heavier the water is, the faster that water's coming out. But once it gets lighter, it's not going to push it out as fast, right? That's what's happening. Okay? All right, so D. So what is the average daily loss of oil that is leaked out over the first 20 days? Okay, underline this word average. Calculus keywords, we see average. And it's talking about the average daily loss of oil. Daily loss means things like gallons per day, right? We're trying to find the average value for our R of t. So this means average value of R of t. And we do average value by 1 over b minus a integral from a to b of our function. So again, we have that. We have that in for y1, so I do my math 9. I can do my vars, y vars, function y1, and I can go from x values 0 to 20. And then once I get that answer, I never forget to divide by 20, right? I'm dividing by that b minus a, the length of the interval, and I get 88.8 repeating. So I'm going to do 88.889 gallons per day. Okay, does all of this make sense? Okay, do you think you could do that on an AP test? I think you could. All right, so sometimes you need to break up the interval. So this happens when the graph hits the x-axis. So we don't know how to integrate absolute values. We haven't really talked about how to integrate an absolute value. So we always sketched it out. And I would continue to sketch it out because it's the easiest way to do this. So think about if you have y equals absolute value of 2x minus 1. And I'm going from 0 to 2. Let's find the heights at 0 and 2. So the height at 0 would be 2 times 0 minus 1. Absolute value is 1, so I get 1. If I plug in 2, I get 5 minus 1, which is 4. Absolute value is still 4. So at 0, I'm at a height of 1. At 2, I'm at a height of 4. Like that. And it's a V shape, right? Does anybody know where the... So let's put in 1 as well. If I put in 1, do you guys see we're also at a height of 1? Where would the vertex be for this V shape? Not at 0. Do you guys see how we have two things that are at the same height?
Oh, no.
It would go directly in between those two. Like that, right? It would go at 1/2. And the reason it goes at 1/2 is because when you plug in 1/2, that's when you get 0. Right? It's like setting 2x minus 1 equal to 0 and solving. You'd add 1, divide by 2, you get 1/2. Right? That's the smallest that an absolute value function can be, is 0. So we end up with two triangles. We have a little tiny triangle there, and we have a much larger triangle here. So we want the area of those two triangles. So the first area is 1/2, base is 1/2, and height is 1. So it's going to be 1/4. And the second area is 1/2. Its base is 1.5. So I'm going to write it as 3 over 2. And its height is 4. So it's going to be 3. Or 12 over 4 if you wanted to get the common denominators. So our total integral, if I have this, is 13/4. Make sense? Okay, so let's think about this. How would we do this without drawing a picture? Now, what I'm telling you is draw the picture. That's the easiest way. Sorry, I'm like so tempted. My twin brother, his wife, is having a baby like anytime. She's due. Oh, is she? Well, they're not having the baby this morning, but like it's due on the 20th, which is Abby's birthday. So Abby's birthday is coming up in a couple days. And so I'm just like patiently waiting, but that was something about the dentist. That's sad. All right, anyway, so if I have a line here, this line, well, let's start with the first line, the one that's positive. Do you guys see how this line is 2x minus 1? It crosses at a y-intercept of -1. It has a slope of 2. What's this line? It's the opposite. In other words, it is y equals negative parentheses 2x minus 1. It ends up being negative 2x plus 1. That's how an absolute value works. It takes the positive bit and then it negates all of it, right? That's why when we solved absolute value equations in Algebra 2, we did like the plus or minus thing. We broke it up. So if I was actually integrating this without breaking it up, I would have to integrate the -1 from 0 to 1/2. And then I'd have to integrate the positive 1 from 1/2 to 2. That would be the way that we would find that. Okay, easier to draw a picture. Do you agree? Much easier. All right, so in order to learn the Fundamental Theorem of Calculus Part 2, we need what's called an accumulation function. So we have this. And we talked about this yesterday, but some of you guys weren't here yesterday, so I'll kind of go through this. So if we have that, and I talk about integrating it, I would integrate lowercase f into capital F going from a to x, which would be capital F of x minus capital F of a. Okay, that's what g of x is all equal to. Capital F of x minus capital F of a. So if I ask you to take the derivative of that integral, so g prime, it ends up being the derivative of this and the derivative of that. So the derivative of capital F of x is lowercase f of x. And what was the derivative of this? Do you remember? This is a number,
0.
so its derivative was 0. Okay, so g prime of x ends up being f of x. So whatever function you have here, we just plug the x in to that function. We learned that the other day on our whiteboard. Okay, so let's see how this accumulation function works. We have not talked about this aspect of it yet. Okay, when you think of the word accumulation, do you guys all think of snow? I think of snow when I hear accumulation. This is kind of like snow. So let's say you started with 3 inches of snow. And after it's snowing an inch, well, let's do 2 inches an hour. After 1 hour, you gained 2 inches. After the next hour, you gain another 2 inches. So I go from 3 to 5 to 7 and so on. Does this make sense? And then let's say it starts melting by ½ an inch after a while per hour, right? You could figure out how that works as well. Okay, that's the same idea that this is going to be. So when you see something that has an x here, this is called an accumulation function. Accumulation. Did I spell that right? Accumulation. Okay, so if I want g of 0, what I'm asking for is the integral from 0 to 0 of f of t dt. Anything from like a number to itself, 0 to 0, 5 to 5, anything like that, what do we get? 0. So if I want g of 2, I'm integrating from 0 to 2 of f of t dt. So what is that? That's representing this area that's under the curve. And that area has a base of 2 and a height of 3. So it's 1/2 base times height. So we end up getting 3. And if I want g of 4, do I gain some more area? Yeah, that's why it's accumulating, right? So I'm gaining even more. I'm saying, well, now I want from 0 to 4 of f of t dt. I just skipped it. You could do that one if you want. So I'm gaining this much. How much more did I gain? Can you guys count these little squares? I gained 6 more. So I had my previous answer plus 6. So I get 9. So what if I ask for g of 5? I gain this much more, right? So I have my previous answer, which is 9 plus 1/2 base times height, which is 3. So I gain 1.5, I get 10.5. Do you see how this works? What do you guys think g of 6 is? Subtract this as well. Do you guys see how those were the same? It's also 1.5. So I take that 10.5 and I go backwards by 1.5. And I'm back at 9. Yep.
Okay.
It's like a rate graph, he's saying. And so if you're losing, like we talked about, like inches per day or inches per minute or whatever, that's what's happening. So g of 8, we're losing some more. This is 1/2, base is 2, height is 3. So we're back at 6. Okay, that's an accumulation function. That's how that works. Okay, and you could have, we've done these a little bit before when we had like the semicircles and the triangles and things like that. Same idea. All right, so Fundamental Theorem of Calculus Part 2 involves taking the derivative of this rate function. So like I said, the easiest way to think about this was like what we just did. The g prime of x ends up being just plain f of x. I actually did that on the previous page. So if I have something that looks like this, and I say find the derivative of an integral, it's like they cancel each other out. So the derivative, g prime of x, ends up being, I want x's, so I take that x and I replace my t's with it. So I do 4x cubed plus 2x. Okay, and I went into a lot of detail yesterday with that, so if you were absent, like Alexa, I know you weren't here, I don't know who else wasn't here. If you were confused, ask me, definitely, if you get confused. So like this one, g prime of x, right away when we see the derivative of an integral, we're like, oh, it's the derivative of an integral, fundamental theorem of calculus, 1 plus x squared under a square root. Do you guys all remember this? Okay. So for number 3, if it's asking about f prime of x, we're like, oh, f prime of x is x squared minus 2x plus 3. So that means capital F prime of 3 would be 3 squared minus 2 times 3 plus 3. So 9 minus 6 plus 3 is 6. Because if you do the antiderivative, so if you do it the long way, it would be 1/3 t cubed minus t squared plus 3t. And then you would take the derivative, which would go back, and you'd still have that 3. Okay? The thing we're getting rid of is this part. See how it's like at 1? Are you saying like what's giving you 0? When you plug in 1 for the second part of that, like if you do it the long way, that second part will be a number. So when you take the derivative, you get 0. So the example we did yesterday to kind of show you guys is what if you have like g of x is equal to the integral of cosine of x going from, it doesn't even have to be 0. That's what I got confused on when I was in school. So I could have like pi over 4 to x. Oh, dang it, I did x twice, didn't I? Make that a t. I do that all the time on this. Okay, so if I went the long way, I would integrate cosine and I'd get sine. And sine would go from pi over 4 to x, which means I'd have sine of x minus sine of pi over 4, which is root 2 over 2. So then if I wanted to take the derivative of sine, well, that goes back to cosine. So it's going to be cosine of x, and the derivative of the second part is always 0 because that was a number. Okay, so as long as you have a number down here, the second part will always go away. It will be 0. But remember, sometimes we have something else down there, like x squared, something like that. So that's when we get into the chain rule. So going back to this example, so Alexa, you missed this yesterday. So if you have like x squared there, if you do this the long way, this would be sine of x squared, right? But when you take the derivative of sine of x squared, just like we did in first semester, we get cosine of x squared times what? 2x. That's the chain. So sometimes we have to do that chain rule. I love that this is almost the exact example I have down there. All right, so that's what's happening here with the chain rule. Whoops. All right, so the long way would be to say, well, I know my g of x function. If I integrate cosine, I get sine going from 2 to x squared. So that's going to give me sine of x squared minus sine of 2. So my derivative then would be cosine of x squared times 2x and then minus the 0. So do you guys see what we do for the shortcut? So if I start out with g of x equals 2 to x squared, and I see that I'm trying to find g prime, so again, the derivative of an integral, that's the fundamental theorem. When I take the derivative of the integral, it's like I still replace, that t still becomes an x squared. So I get my cosine of my x squared, but I have to multiply by the chain. And that chain is always the chain of whatever was on the integration symbol, the elongated s. So it's the chain of x squared. So if you're plugging it into a square root or x cubed or whatever, that's okay. Just do the chain of x squared, its derivative is 2x. Okay. And you can go through the long way if you need to, but sometimes we have ones that we don't know how to integrate. So like something like this, I would say, oh, it's the derivative. It's going to be cosine of x cubed times 3x squared. Done. That pi over 2 part doesn't matter. But in number 6, notice how I'm not asking for a derivative. There's no like d dx in front of it, d over dx. That means derivative. It doesn't say find the derivative of this integral. This would just be, so no derivative. This would just be, you know, integrating sine of t, getting negative cosine of t going from 0 to x. This was an actual AP question one time. So a lot of students were like, oh, it's a fundamental theorem. It's just going to be sine of x, right? Do you see how it's different? There's no like derivative that it's asking for. Okay, I'm seeing blank stares. Do you know what I'm saying? It doesn't say find the derivative of this integral. It doesn't say find g prime or anything like that, right? So we plug it in. So we have negative cosine of x minus a negative cosine of 0. So it's negative cosine of x minus a negative 1, so plus 1. Okay, but this one, number 7, goes back to derivative of an integral. This is a fundamental theorem. Anybody think they know what this one is? Cosine of x cubed times. And how did you know that you had a second part to this one, Abby?
Because there's an x on the bottom.
Yeah, there's no like number on the bottom, so that second part, which we would have taken the derivative of, isn't going away. So we still have like our minus our second part. So plug in the x squared. So this one, if I start out with a number, that first part will be 0. And then minus, now I plug in the x cubed. So minus sine of x cubed times 3x squared. So it's just negative 3x squared times sine of x cubed is how I'd write that answer. Okay, and then the last one was a true AP question. I know I'm going like 1 minute over. Can you guys live? All right, so if I have this f prime of x, my clock is a little bit off. It's not actually like 5 minutes over like you're thinking. Okay, so we do e to the 3x squared times what? What's the chain? 2x, right? Okay, so it's not 6x. A lot of people will put 6x because they're like, well, we plugged in x squared and got 3x squared. Right, it's always from here. And then we do f prime of the square root of natural log of 5. And that's where it gets a little bit messy because we have things like the square root of natural log of 5 squared, right, to square root of natural log of 5. And what's tricky with logarithms, as we talked about before, is the AP test will simplify them in strange ways, or they'll simplify all the way down, and you might have something else. So if you see something like this, we have e to the 3 natural log of 5 times 2 square root of natural log of 5. And at first glance, you're like, ooh, I really want to cancel those. But you can only cancel it if you have the e and the natural log right next to each other. Like if I had e to the natural log of 7, that is 7. Can I get e and natural log next to each other in this case?
Cube 5.
Yeah, I can cube that 5. Do you guys see it? This 3 is going to go up as a power. It's already in the front of a logarithm. Some people were saying yesterday, oh, it's going to go in the front of e. It doesn't go in the front of e. It goes in the front of a natural log or a log, which it is. It's in the front of a logarithm. So we bring it up as a power, and we get e to the natural log of 5 cubed, which is 125, times 2, and then the square root of natural log of 5. That's how they would get those cancel. E and natural log 125 times 2 is 250. So 250 square root of natural log of 5 is the answer. Okay. A answer. Yeah. There are other forms of that answer, but that's probably the form they have it.